Hello, my name is Sergei Kosulnokov. I am from Aalto University, Finland, and now I would like to share with you our short tutorial on metasurfaces design and manufacturing, which we are working on as a partner of Ariadne project. Our task was to find reliable solutions for the perfect anomalous reflectors which can be utilized as a part of novel wireless technologies. As a given task, we had to find reliable design for this given set of frequencies operating at the incidence angle of 50 degrees and anomalously reflecting the signal towards normal direction from the metasurface. As the final realization, our plan is to put these three perfect reflectors, as presented in this collage, on a wall, which can allow to enhance connectivity between separated transmitter and receiver utilizing millimeter wave directive antennas. Several years ago, in our group, demonstrated how it is possible to realize an optimization procedure to find the properties of the metagrating reflectors, and this theoretical code allows us to operate with the reflection properties of these structures. At the end, numerical optimization minimizes the cost function between the desirable, between the realized values of the reflector and the objective properties of those. As one of the features of that realization was that the surface impedance was realized as a continuous function, whereas at the end, when the realistic structure should be implemented, one should discretize this surface as a set of discrete elements, and this discretization, in fact, affects the final properties of the scatterer, which are different from the initial predicted continuous function. Whereas in the updated design, which we work with Ariadne now, we applied a different procedure, whereas our surface impedance values function was realized as a step function, and intersection of these steps allows to excite additional scattering harmonics, which we utilized in the result scattering, and optimization procedure at the end grants the results which are much easier to be implemented straightforward after this theoretical optimization procedure. As the output of this numerical optimization, we observe magnitudes and phases of the desired propagating harmonics and also higher order evanescent harmonics. Here, in frame of this particular task, our goal was to maximize first propagating harmonic and minimize 0 minus 1 harmonic, and also to pay attention that these higher order evanescent harmonic are decreased. With the given solutions, we get a number for the surface impedance, which should be realized using different topologies of the elements. Considering the topologies, initially, we tried to utilize the simple capacitive gap as the subcell elements. However, we realized that this type of structure grants a very high difference between the surface impedance properties, considering normal illumination and reflection coefficient and oblique illumination and reflection coefficient. We found that more complex design of these unit elements realized with the so-called dog bone allows us to get, on one hand, much better angular stability. So you see the difference between the line for the normal incidence and the oblique incidence is almost negligible in this case. And on the other hand, different realizations of these side dimensions of the part of the dog bone allow to cover a very rich range of these realized surface reactance. At the end, we found which particular properties of these dog bone elements, and also we just to notice we had to use a strip element to realize a positive impedance at one unit cell, in particular for this design number one. So what should be these dimensional properties of these sub-elements in order to satisfy the desired surface impedance? In order to get more details about these dimensional numbers, please follow up the publications on the website of Ariadne project. However, in the simulations analysis, our full wave simulations for the infinitely large periodical structure proved that the structure operates as an anomalous reflector, and taking into account realistic losses within the dielectric substrate and final conductivity of the metal, one can achieve an efficiency of 90, almost 91% for anomalous reflection. Also, before going to the manufacturing process, we checked how variations of the dimensional parameters, variation of the substrate thickness, and accuracy of the operating frequency affects the performance of this anomalous reflection, and we found that in a reasonable wide range of these values, structure still grants a very high value of performance. Please follow the updates of our activities at the website of Ariadne project. Thank you very much.